little bit behind the schedule, so thank you again. And I will leave the floor to the next speaker, that is Professor Cao from the Cagliari University, that will speak about ZTAR, HF, and TA-based ultra-high temperature ceramic for thermal protection systems.
I don't see my presentation. Prego.
We need some help.
Just a little problem with the computer, but no problem. Mr. Pinelli, please.
We are very far from hypersonic.
No, ma non c'è la presentazione, capito? Quello l'ho già fatto.
Cosa non avrei dovuto fare?
Ah, ok.
Avete chiuso TeamWeaver? Eccolo qua. Ok, questo facciamo Alt F4. Alt F4. Ok?
Il pointer funziona, sì?
Sì, sì, sì.
Funziona come?
Questo tasto centrale.
Ok.
Ok?
All right. Well, thank you very much. Mr. Chairman, ladies and gentlemen, it's a pleasure to be here. I would like to thank the organizer for this invitation, which we did accept with great enthusiasm. I'll be talking about zirconium, hafnium, tantalum based ultra-high temperature ceramics for thermal protection system. You might know that these materials are considered to be very interesting for their unique properties. These properties are like high melting point, good thermal shock resistance, and particularly resistant to ablation in oxidizing environment. So if you take a look at the production of these materials, what you see in the literature is that conventional techniques for producing starting powders give rise to low sintering ability. If you take a look to the consolidation techniques to sinter the starting powders, like for example hot pressing, then you get very much severe sintering conditions, and typically what you get is a coarse microstructure and high production costs. So what is typically done is to introduce suitable sintering aids, as some of them are listed here. There are, of course, alternatives to produce these materials in a better way, I would say. One alternative is to produce starting powders with improved sinterability and also use more efficient consolidation methods. So I'll be talking about one technique to produce powders with improved sinterability, which is called self-propagating high temperature synthesis. And I will be also talking about a relatively novel, innovative consolidation method, which is known as SPS, spark plasma sintering, or electric current assisted sintering. As far as SHS is concerned, typically you have a reactant, then you ignite the reactant powders, then you get in a very fast way through a propagation front the product. And at the very end, you can get very high velocity, and you can also get very small induction time for ignition. It is very well known that SHS powders are very good in sintering. So in the early 20s, there were tested 3 different techniques, and at the very end, all the powders produced through these techniques have been sintered under the same conditions. What you get is actually that the relative density of the material at the end is much better if you take into account SHS with respect to the other technologies. And the reason for that is that if you through TEM, you go and look at the defect density, basically SHS technology is providing a concentration of defect density much higher. And this is due to the fact that you can get heating of this value and cooling rates of such values, which are not reachable by other techniques. There are, of course, in the literature very many applications of like sintering of SHS powders, which I'm not going to go through. But let's go and talk about this relatively novel sintering technique. This is known as SPS. So basically what you do is you let the current passing through the die, which is typically made of graphite. In such a way you could get a dense product, and you can reach classical sintering purposes, but you also can make reactive sintering results. So if you compare these 2 techniques, the conventional hot pressing technique and the SPS, well, basically what you have, if you take a look at these 2 pictures, is that you have an external, in this case, or a direct powder die eating. So at the very end, what you get is that with the SPS, sintering phenomena are promoted. You have very much shorter processing time and finer microstructure. We have been showing results that we have been obtaining with this machine. As far as you know, this is the very first machine that came in Italy, 2003. At this point, there are only 3 machines in Italy of this type. 2 of them are in Cagliari. There are about 20 machines of this type all over Europe. In 2001, when we started working on this technique, there was only 1 machine in US at the University of California, Davis. So if we consider this system, which is not the system I'm going to talk later on, you will be seeing by comparing the 2 techniques that you take the sintering, you reach the sintering under lower temperature, under shorter processing time. You have an energy saving of the values of 1 order of magnitude, which is very important in terms of cost that have been discussed by previous presentation, and you also have better properties. Okay, so let's confine a little bit more our attention on this ultra-high temperature ceramics. They have very much application in the aerospace industries. We are talking about typically nose caps and leading edges, but there are also other applications that are very interesting. One is solar absorber, and the other one that I would like to talk about is to mention is the molded metal crucibles. Our spin-off company from the University of Cagliari has put in the market right this year the first crucible made of this material, which was not available earlier on the market. So let us consider now a couple of cases, then I can skip if I am out of time. So let's talk first about this complex system here, this zirconium diboride, zirconium carbide, silicon carbide system. So you prepare by SHS the powders through this reaction. Then, of course, you can see that you get the complete conversion. And then you process them by SHS. And if you, by SPS. If you process them by SPS, what you get is actually, you get a microstructure of this type, and you get a fully dense product, and you get mechanical properties that are really very much comparable to the best results reported in the literature. If you take and if you compare the sinterability of these powders we have been producing with the commercial powders, well, there is no match, because look, you can get only 90% density, relative density. So what is the reason for that? So the reason for that, even if our SHS powders are coarser with respect to the commercial mixture, then each SHS particle consists of various grains of boride and carbide, so there are very strong interface, so the distance are reduced during the sintering. That's the reason why we get better results. Let's take a look at another system. So here what you can do is this. You can produce the powder in two ways. You can go directly to obtain in one stage the two components, or you can have a two-step synthesis, so you can like synthesize the two components separately. Just take a look at the fact that there is an excess of boron in the mixture, and this is required because there are certain losses during the SHS reaction. So basically, you complete in both cases the reactant conversion, and you get similar particle size powders. On the other hand, if you just go and make the sintering of this powder, well, you get the difference. So basically, you have a much better sintering ability if you produce simultaneously the two constituent phases, if you obtain simultaneously the two constituent phase in situ. So there is a very much strong importance of the formation of interface. Let's take a look at another system, diboride, zirconium diboride, silicon carbide. So in this case, you have two possible processing routes. One is the so-called direct RSPS, so reactive SPS. You consolidate and you react the powders, the starting powders, in one time. Or you go through, say, route 2. So basically, you get the products through SHS, and then you sinter them. Let us see what's the how to compare these two, say, processing routes. The first one is the reactive SPS. So what you can see in just 8 minutes, then you get through a gradual solid mechanism, you get the full densification. With this is the total time. Of course, that is the conversion in 8 minutes. But out of it, 30 minutes is the entire time to get the complete reaction and the densification of the product. So this is actually the microstructure of the product. You get the complete reactant conversion, and again, as in the previous case, SHS particles are constituted by zirconium diboride and silicon carbide, which is what we want when we go to sinter. However, if you take a look here, what is interesting to see is that it is definitely much better to go and to produce powders by SHS first, and then to sinter them by SPS, because you have relatively milder sintering conditions. Just take a look at here to obtain the maximum relative density. Let me go to just another example, which probably is the last one. So one more thing that you could do is actually, if you take a look at this diboride, zirconium diboride system, this is a very recent result. And if you just have an extremely reactive system, as this diboride is, then what you can see is that in a very short time, see tau 1, tau 2, you see how the composition changes abruptly from, say, 1.5 minutes up to 1.7 minutes of synthesis, then you do get such a difference, which is quite interesting from the scientific point of view also. So the drawback you have when you do combustion synthesis under reactive SPS is the fact that typically you have an increase of pressure. In this case, you have a volatile species, the boria, which is developed during combustion, and actually you could have powder expulsion from the reacting mixture. You could have products inhomogeneity and so on, and also safety problem and difficulties in scale up. Just to give you here an overview of the main characteristic of these powders we have been producing by a combination of SHS and SPS. As you can see, and if you know the literature, the values in the literature, so we are definitely better in terms of hardness. We are similar in terms of fracture toughness. But what is interesting is that we have been testing these materials also as far as their capability of sustaining high temperature oxidation environment. And here you can see from the various acronym of the various composition we have been working on, you can see the difference. They are all quite good for potential application in hypersonic vehicles. So what's the rationale? That has been discussed in the literature quite well by several colleagues. Well, basically what you can get is the fact that you have this boria basically is forming a silica-rich borosilicate glass layer, which is basically doing is acting as a diffusion barrier and also is increasing the oxidation resistance of these materials. So let me go to a few concluding remarks. So we have been actually showing that if you produce the powders to be sintered by SHS, remember, self-propagating high temperature synthesis, what is good is that you get powders that are very sinterable. Powders that can be sintered quite easily, and the reason is that stronger bonds are established at the interfaces between these powders. If you take into look at the spark plasma sintering as a possible potential technique to sinter this material, basically at the very end what you get shortened time and you get sintering lower sintering temperature, and this is of course is a reduction of costs. But pay attention when you work and you synthesize and you sinter this material, pay attention. Try not to go to the reactive spark plasma sintering, particular if you go under the combustion regime, because there are very many inconveniences that you want to avoid. On the other hand, if you follow a gradual solid state mechanism, then you are safe and you can produce these powders through these methods too. Thanks for your attention.